Okay, let's try this with machine learning. So first of all, let's check, is this ready for machine learning? Right, we have our data frame. So what is the info on it? You can see that there are all columns here under D types, okay? We see that there are 3,197 columns are float 64s and one is an integer 64, right? So all columns are numeric. And it doesn't tell us here if they are in itself, if they're null values. So df dot, is it df is null? And I think we want to sum this twice. Because I think the first sum gives you the individual columns. Let's see if that's right. No null values. Okay. Double sum because it's the first sum just gives you to you by column. Okay, so all columns are numeric and no null values, which means it is ready for machine learning. Now it's already split into X and Y, but just to show you, like if you go up to the data, right, the first column is the Y, okay, that's right here. Mark df label, right, that's how you access a column. And the X column is everything else, so it's all rows and starting with the first column. Okay, we're not going to use cross-validation on this data set just because it's so large. I want it to be 5 times faster. And so we'll just do one training and test set. Okay. All right, so let's get ready now for machine learning. So first of all, let's import XGBoost. And we're going to go ahead and import the XGB classifier because it's classifying it into 2 groups. We also want train test splits, so that's from sklearn.model selection, import train test split. And I think we also want to go ahead and import, get accuracy score in here. So from sklearn.metrics, import accuracy score. Now, as I hinted at the end of last time, accuracy score is not going to be good enough, but that's the normal starting point, okay? So let's see how we do with it. All right, so go ahead and run it, and now let's go ahead and split the data. So X train, X test, Y train, Y test equals train test split. Now, I realize, okay, so look up here. Do you see where it says stratify equals none? So stratified data means that it's going to have the same number of the same percentage, I should say, of, affirmative cases. And that's important here because, there are only 37, affirmative cases. So we want to stratify it on the Y. So I think that's how you do it if we put stratify equals Y. Never done it like this, so we'll see if it actually does work. Make a note here. Split data, and then stratify Y to ensure same percentage of exoplanets. Again, that's our Ys. So does that do it? Didn't do it. It might be the way, is it the way I'm calling out? Wait a minute. I jumped the gun. We still need X comma Y, right? We didn't, that's the normal input. And get overexcited about this stratify Y things. Try it again. Okay, it seems to work. Now, how can we verify that? Well, let's try, okay? Right, every time if you write code and it's doing something, you want to, if you haven't done it before, you want to make sure that it's working as expected. So if I go to ytrain.valueCounts, okay, you can see it's got 28 exoplanets and 722 non-exoplanets. And so now if I do ytest.valueCounts, I get 9 to 241. Now, are these the same percentage? Okay, you could divide those numbers to find out. Here's how I do it. I say, well, you know what? 28 is about triple of 9, and 722 is about triple of 241. So I'm just going to be satisfied that it did what I wanted it to do. Okay, that's excellent. And I do want to underscore the importance of that here because, like just imagine that, I don't know what it would do. We could find out, right? Like if we don't stratify it, you can change the code. But imagine this one had like 34 and this one had 3. Well, it's not going to test well, right? You want it to have the same percentage, I would say usually always, but especially if you have imbalanced data. Okay. So now that we've split it, let's go ahead and see what we can get with just a default XGBoost model. Okay. So build XGBoost model with accuracy. All right, so how do we do that? Let's define model as the XGB classifier. Now we're going to fit it, okay, on the X train and Y train. Right, so this is our training set, right? And what it's doing here is it's trying to match like all the correct inputs to the correct outputs, which are here they have 722 ones, 28 twos. But now we're going to get the predictions. So what are the predictions that the model that was just built in the line above, what does it give us? Well, it's model.predict X train. So that gives us the predictions, right? Some of them probably match correctly to Y train, but probably not all of them. I'm sorry, we want to do an X test, right? Because we could score it on the training set, but right, we've talked about this. We want to score it on the test set. And so now I want to get the accuracy score. I want to compare the Y, and there it's giving us the correct order. Do you see that up there? It does actually, it's going to matter going forward here. So we want Y test and then Y prediction. Okay, it's very important that you understand those lines of code. Okay, so let me just go over them one more time. When I write model equals XGB classifier, what that does is it just creates a default model. It creates like a generic initializer, really, and it's got all the standard defaults because I didn't make any adjustments here. Okay, I could put in a random state for you to match my code, but let's get different scores. And now what it does is it takes that model, and this is where the machine learning happens, and it fits it so it's trying to match the training X's, all the inputs, with the correct Y's, all the outputs. And it does that using like 100 decision trees, because that's the default. And it plays the games of 20 questions for each decision tree. And then it's gradient boosting, so it fits on the errors. It fits on the residuals. Okay. And my point is that this is where the machine learning happens. Okay, after it's done, we want to see how to do on the test set. First, we get the predictions. Okay. So it's model.predict on, right, we're feeding in now some new data, but all data goes through the model, as long as it fits the same kind of X's. And so it's going to give you predictions. So now at the last line, we simply check, okay, well, how many of those predictions are correct? We get a percentage, okay? Shift enter, I should have explained that as the code was running. Shouldn't take too long. Now, granted, it is 100. We did talk about time. It is 100 decision trees here. You can see it's actually taking a little time. Not too bad though. So 96%, right? Solid, okay. But here's the thing. When you have imbalanced data, you cannot jump the gun and assume that that's a good score. And here's why. Okay, if you look at the test set, so it shows 9 out of 241. Okay, what is that? What is 9 divided by 241? Look at that. It's 3.7%. So do you see like this the issue here? I can say, you know what? I'm just going to build a model that says everything's not an exoplanet. And if I do that, I will only get 9 of them wrong. And so correct will be, I could write, if you can't do the math, you can code it. I can usually do 241 minus 9, but it's kind of fun that you can do it like that too. I will get 96.3% correct. So basically, this score, okay, at the outset seems good, 96%. In reality, I just wrote a model that got 96.3% rounding, right? Simple, just everything's an exoplanet. I mean, not an exoplanet, everything's a 1. And this is why, oh, wait a minute, maybe accuracy isn't the best score. It's even worse if it's more imbalanced, right? If you have like 99.9% like of one thing and not the other, then if you just pick all the other, you're going to get 99.9% accuracy. Congratulations, you win the prize. But your model sucks. And you want to build good models. And it's even worth thinking about, what do you want to do with the model, right? No one wants to predict no exoplanets. We're looking for the exoplanets. We want these. And so we need different scoring metrics, okay? Because let's just assume, right, that, I mean, it's titled Discovering Exoplanets. That's why people are looking at the stars. It's not that there's no value in, like, which I think would actually be a much harder thing to do, to confirm that there's no exoplanet. Like, that's tough. Like, what does this mean, these 241 ones? That doesn't mean that there's no exoplanet there. That means that none have been confirmed. Okay? I say that because, like, if you have a small planet like Mercury size and a distant star, you're probably not going to be able to detect any light fluctuations, but that does not mean that there is not a planet there. Okay? The key is that it's confirming the existence of exoplanets. And this is huge. And this is one of the greatest accomplishments of astronomy transferring into the 21st century. It's the rise of the discovery of exoplanets. And what we're going to look at next is how to adjust accuracy score. We're going to look at different metrics to try to improve things.